So this is the video about linear congruence. In this video, I will try to explain the basic definitions, and there is a important theorem about linear congruence. That means actually not all linear congruence can be solved, and we have some criteria in solving linear congruence, and that is given by the theorem. Okay, and then there are examples, and I will illustrate the method in solving linear congruence as well as the methods, okay, through those examples. Okay, so this is the purpose for this video. Now let's just begin with the very basic definition. So what is the meaning for linear congruence? Well, this is the definition. So for example, we let a and b be integers and m be a positive integer. So actually they're all integer, but m has to be positive. Okay, so we say a congruence, or you just simply say linear congruence, a congruence of the form ax congruence to b modulo m, okay, where x is an unknown integer. Okay, so not just an unknown, we have to require x to be an integer. Then if we have an equation like that, then this is called a linear congruence. So more specific, to be more specific, this is a linear congruence in one variable. Okay, so that's the basic definition. So in other words, we have a, b, m, they are all given, but x is an unknown. So we have to solve x from the equation. So just an example. Okay, so for example, consider, okay, let me just go down a little bit. Consider 2x congruent to 1 modulo 5. Okay, so then you see we have numbers 2, 1, 5, and x now is a variable. So we have to solve x, okay, from that equation. So this is a linear congruence. And you can try to solve it, because this equation is not that complicated. Okay, especially those numbers are small. You can, for example, try an error and see that x equal to 3 is a solution. Okay, you just try. Okay, we can check. Okay, even check. Okay, so we multiply 2 by 3, then we get 6, and it's easy to see that 6 is equivalent to 1 after you take the congruence 5, because 6 minus 1 is equal to 5, which is congruence to 0. So x equal to 3 is a solution. Okay, and notice that in fact not just 3, you can add any multiple of 5, okay, to the solution of, you must have one solution, and then you add multiples of 5 to that solution, then you can generate some other solution. So in particular here, x equal to 5, x equal to 3 plus 5k, where k is any integer that also solve the equation. So solve 2x equal to 1 modulo 5. Okay, you can check it. Okay, again, it's very easy to check it. For example, you substitute it back to the equation. So, 2 times bracket 3 plus 5k, and that give me 6 plus 10k. Okay, and remember, because you are taking congruence with respect to 5, so of course 10k always give you 0. So that congruence to 6 modulo 5, but that is also equal to 1 modulo 5. Okay, so that's why it solved the original problem. Okay, now here's the question: how can we solve it? Okay, of course, for that kind of simple problem, we can just by observation, by trying and error, you can always solve the problem. And but not all problems are that trivial. In particular, how can you get all solutions? So for example, how can you know that here we have to add 5k to the solution, then we can get all other solutions? So how does it work? Okay, so this is the problem. In fact, we have a theorem. Okay, so let me just write down the theorem. So this theorem is important. That is the important theorem I mentioned on the outline. So let's see how and why this theorem is so important. So let's say we have a, b, m be integer. Okay, they're all integer. And of course, we take m to be positive because actually m is the base. I mean, not the base, but the integer we are taking congruence. So we are congruent with respect to m. So that's why we have to take m being positive. And we let d to be the GCD of a and m. Okay, so just a symbol. I mean, just for simplicity, we take the GCD of a and m just equal to d. Okay, because we don't want to refer back. I mean, always refer back to the GCD, but just take that to be d. Okay. Then for the equation, ax equal to b modulo m. Okay, let's just call that to be star. Okay, just call that equation to be star. Okay, so then we have two cases depending on how we have the relation between d and b. Okay, now first case is if the GCD of a and m, which is d, is not a divisor of b. Okay, if that is the case, then the equation star has no solution. This is the first case. Okay, so you should be very happy if you find that, okay, the GCD is not a divisor for b, then okay, done. Okay, we don't have any solution. Okay, but if not, okay, for example, if we have d is a divisor, okay, you only have two cases, right? Either d is a divisor or not a divisor for b. So that's the other case. If d is a divisor for b, then the equation star has exactly d many incongruent solution. Okay, when you're taking more the congruence with respect to m. Now, actually, you will see it. Okay, in the sooner or later, in a minute. Well, even though I said the solution has exactly d many incongruent solution, in fact, because you're taking congruence, okay, if you're not considering congruence, you should have infinitely many solution. Okay, so actually that is very similar to the linear Diophantine equation you learned in the previous chapters. Okay, and because we learned congruence already, so we can consider solution or problem with respect to congruence of some number. Here we have m. Okay, so that's why we can say, or we can quantify the number of solutions in terms of congruence with respect to that integer m. So that is something different, but in some sense that is more convenient, because you're not just keep saying, well, we have infinite many solution, but now you can say, well, if I classify them into congruence set, okay, or you just say congruent solution, actually there are not many. There are just d many incongruent solutions. So that means you sort of subdivide those solutions into different classes, okay? And here you only have d many classes, even though there may be infinitely many solutions. But if you subdivide those numbers into classes, then you only have d many. So just a quick example. For example, you know that integers, okay, you can only have even or odd numbers, right? So even though you have infinitely many integers, you can divide them into two classes, even or odd. Okay, so a similar case just happened here. Even though you have infinite many solution, but you can divide them into finitely many classes in terms of incongruent solution. Okay, so d many incongruent solution, that means d many classes. Okay, so that is the theorem. Of course, if you look into this theorem, okay, of course, the more important part is the second part, okay, because the second part tells you exactly what's going on about the solution, okay. But here I haven't told you what are the solutions, okay. But well, we are not in a hurry, so I will show you the details step by step. Okay, so before I give you the proof, okay, so before we prove the above theorem, let's just look at the following example. Okay. Now, what example? Now, for example, find all. Okay, that is important. Find all solutions to 3x equal congruence to 12. Okay, module 6. Okay, so we try to solve that linear congruence equation. Okay, and how do we solve it? So solution is the following. So this is a more systematic way in solving the problem, rather than just by observation, by trying and error. Okay, that is not systematic at all. Okay, because if you're lucky, then you can get the solution without much difficulty. But if you're not that lucky, then what should you do? You just have to keep trying. But in fact, you don't have to that silly. Actually, there's a more systematic way to solve the problem. Now here is the solution. So to find one solution, so you first find a particular solution. Okay, one solution. Now we solve. Okay, we solve another problem. Well, actually, as I said, it's quite related to linear Diophantine equation. That's why we solve this linear Diophantine equation here. So we solve x0, y0 from this problem. X0 plus 6 times y0 equal to 12. Now, rather than solving that linear congruence equation, we are trying to solve the Diophantine equation first. Okay. Now you can see. Okay. So why do we have to solve it? Because now if you have a solution for that linear Diophantine equation, which actually you have two solutions, x0 and y0. Okay. But in fact, if you have that solution, you can sort of discard the y0, because actually we only need x0. And from that problem, or from that equation, x0 will solve your original problem. Okay, so this is a remark. Okay, so why? Because, so just a quick remark. In fact, we can readily see that x0 actually solves this problem. So let me just use copy and paste. I don't want to type. Okay, you can check it very easy, because after you take the congruence from module 6, that 6y0 just gone, right? Because it's a multiple of 6. So that's why 3x0 must be congruent to 12. Okay, because of that thing. Okay, now that means now A more reasonable way to solve the problem is to first solve the linear Darwin equation. Now, how can you get this 3x0? I mean, 3x plus 6y equal to 12. Well, actually, 3x is already given in the original problem. But how can you get the 6y? Okay, okay, but this is quite easily. I mean, you can easily see that from the problem because you are taking congruence with respect to 6. So that's why even though you add any multiple of 6 to the equation, that equation is sort of like equivalent to the original congruence problem. I mean, the linear congruence problem. Okay? Anyway, so now, how can you solve it? Okay, I mean, for the linear Darwin equation, you can have many methods. For example, you can use Euclidean algorithm, okay, or by observation, whatever, okay, because that linear Darwin equation is quite easily to be solved, okay. Now you just have to find one solution, okay. Remember, you don't have to get all solution for the linear Darwin equation, okay. So first, we get x0, y0 first, okay. I mean, for that problem, we get x0 equal to 6 and y0, you can take that to be minus 1. Okay, anyway, y0 is not important. So x0 equal to 6 is also a solution to, solution to 3x equal to 12 congruence modulo 6, I mean. Okay. Now we got one solution already, right? It's not that difficult because once you understand, okay, you can transform any linear Darwin equation in that form linear congruence equation in that form to a linear Darwin equation, okay? Then once you can do that, then it's just a problem for the linear Darwin equation, and we learned a lot already from the linear Darwin equation from the previous chapters, so it's not that difficult. Okay, now we got the solution. Then notice that, okay, you can take x equal to x0 plus, okay, 6 divided by 3 times k. Now I'm not saying, I mean, I will give you the reason later on why we have to take 6 over 3, okay, but you can check, okay, if you take x equal to x0 plus 6 over 3 times k, that is k plus, 6 plus 2k, and k is any integer, okay? If you take it in that form, then it solves the problem 3x solve this, okay, as well, okay. Again, you can check it very easily, okay. For example, you substitute it back to the left hand side, then you get 3 times 6 plus 2k, okay, and that is 18 plus 6 times k, okay. But that is exactly congruence to 12 modulo 6, okay, because 18, you know that 18 is congruence to 12 modulo 6, and the 6k is just congruent to 0 because it's a multiple of 6. So that is clearly a solution, okay? So we have a more general solution. So therefore, in fact, we already got infinitely many solutions. So therefore, x equal to 6 plus 2k for k being any integer gives all the solution to the problem 3x equal to 12. Okay, modulo 6. Okay, so we got all solution already. Okay, but of course I haven't shown you why it will always give you all the solution. Okay, I'm just saying, oh, they should have, I mean, they should give you all the solution, but what is the reason? Okay, so I have to give you the reason as well. But at this moment, this is the solution for the problem. Okay, so let me just give you more details for this example before the end for this video. I mean, for this part. So just a remark. Okay, so among the solution, okay, you can take two, I mean, not two, but actually you have some special solutions. So for example, now you can check x0 equal to 6, okay? That is the solution you got at the very beginning. So x1, for example, you take k equal to 1, okay? That will give you 6 plus 2, and that will give you 8. x1 equal to 8, and for example, x2, that is 6 plus 4, that is 10. So now actually you can start writing different solution. So if you look into the solution more carefully, okay, you can see that actually these three solutions, okay, they are incongruent solution. Incongruent solution. Incongruent solution means they are not congruent with respect to the congruence module 6. You can check it. For example, 6 and 8, they are not congruent in the sense of the congruence relation 6, because 6, for example, you take the difference, 8 minus 6, that is just 2. So that is not a multiple of 6, so that's why 6 and 8 is not congruent or incongruent, okay? And similarly for example, for another pair, you can take 10 and 6, okay? Then 10 minus 6, again, is equal to, 10 minus 6 just give you 4. Again, it's not a multiple of 6. So that's why they're incongruent. But how can you get those incongruent solutions? Okay, it's not just by luck. Okay, actually, there's a way to write down all the incongruent solution. So I will give you the details in the second part of the video.